Let's consider our zinc-copper redox reaction. And if we separated the two half reactions in two different beakers, filled them with water, and then if we have, say, a zinc solid electrode and a copper solid electrode, connect them by a wire, and we have our salt bridge. And we have zinc going to zinc 2 plus, giving up 2 electrons. These 2 electrons will travel through the wire to the copper electrode, where copper 2 plus can bump into the electrode and gain those 2 electrons and plate out as copper metal on the electrode. And then we can balance the charge by letting negative ions move through the salt bridge. So this is a way for us to separate the two half reactions and have the electrons flow through a wire and get something useful out of that current. Now, why do electrons flow through the current? Well, you're very familiar with the gravitational potential. So if I drop this marker, it will fall due to the force of gravity. And there is an electrical potential due to the attraction and repulsion between electric charges, and it produces a force just like the gravitational force acting on my marker, and it will move the electrons through the wire from one beaker to the other. And we can measure this potential or this force, and we call it the cell potential or the electromotive force, or EMF. We'll call the cell potential V and measure it in units of volts. And if we applied a voltmeter on the 2 electrodes, we could measure the difference in electric potential between these 2 electrodes, just like you can plug a voltmeter into an outlet in your wall, and you would see a difference in potential of about 120 volts for your house. We could measure the difference in potential between the 2 electrodes, and we would find that the potential is equal to 1.1 volts. So there's 1.1 volts in potential difference between these 2 electrodes, and that is what drives the electrons from one beaker to the other. So depending upon the half reactions we have, we can vary the potential difference between the 2 beakers. So you can have batteries that have different potentials. If we want to know the difference in potential between 2 redox half reactions, it's convenient to make a table and reference them to something. So what we're going to do is we're going to pick a reaction and we're going to reference all of the other half reactions to it. So we'll build a cell like this, and in one side we'll have a particular half reaction, and then the other side we'll have various half reactions. We'll measure the cell voltages, and then we can make a table and reference to that particular half reaction. And the particular half reaction that we're going to use is called the standard hydrogen electrode, abbreviated SHE. And in the standard hydrogen electrode, we're looking at this half reaction. So we take H plus, we reduce it with an electron to produce the hydrogen atom. So this is the standard hydrogen electrode half reaction, just the reduction of H plus with an electron. So we can construct a beaker, and since we don't have a solid like with zinc or copper, we need another electrode, and we usually pick platinum because it's very inert and unreactive, and it won't react and be consumed in the reaction. So we have our platinum electrode, and we're going to have H plus in solution, and we'll have H2 in the gas phase, and our wire connected to the electrode, and so H plus can gain an electron on the platinum electrode, and then H2 will bubble out of the solution. And then we can put another half reaction in another beaker, and then we can measure the cell potential, and we'll measure it all relative to the standard hydrogen electrode and then make a table, and we call this table standard reduction potential. Okay, here I have just a few entries from a large table of standard reduction potentials. So these are all relative to the standard hydrogen electrode, and the standard hydrogen electrode is given a half reaction potential of 0. So this is all relative to the standard hydrogen electrode. So we set it equal to 0 for convenience, just like we set the freezing point of water equals 0 centigrade for convenience. So this is a relative scale relative to the standard hydrogen electrode. So these are the half reactions, and if we put, say, the copper in one side, this copper 2 plus reduction, and the standard hydrogen electrode in the other side, and measured the cell potential, it would be 0.34 volts. Everything's relative to the standard hydrogen electrode. And if we look at the values, some are positive, some are negative. So what does the negative mean? It means that the reaction actually runs backward relative to the standard hydrogen electrode. So instead of a reduction, it means an oxidation occurs when I have the standard hydrogen electrode in the other beaker. So positive cell potential means the reactions run forward. Negative means the reactions run in the reverse relative to the standard hydrogen electrode. So if I wanted to know the cell potential between two particular reactions, I could just look at the two reactions and then add the two potentials. One has to be an oxidation, one has to be a reduction though, and in this table, this is standard reduction potential, so every reaction is written as a reduction, so gaining electrons. And what we mean by standard is that all concentrations are 1 molar, so whenever you see aqueous, it means that the concentrations are 1 molar. Whenever you see gas, it means they're at 1 atmosphere pressure above the liquid. So that's what standard means: 1 molar concentration, 1 atmosphere pressure for the gases, partial pressure for the gases. So say I want to know the cell potential between my copper and zinc half reactions. So I would have, in my cell, I have an oxidation and a reduction. Something's losing electrons, the oxidation, and something else is gaining those electrons. That's the reduction. And so I'd have E for the cell, and I use a little superscript O to represent standard. So it means 1 atmosphere pressure for the gases, 1 molar concentrations for the dissolved species. And this is how the table is developed, using those concentrations and pressures. So E for the cell is equal to E standard for the oxidation plus E standard for the reduction. So if I look at my half reaction, say I want the copper and the zinc. That's my reaction I was looking at before. Zinc being oxidized, copper being reduced. So in my reaction, zinc was running backwards. This reaction, zinc was going to zinc 2 plus, and copper 2 plus was going to copper. So when I look at the oxidation, since this reaction is written as a reduction, I have to go backward, and so when I go backward, I change the sign of the half cell potential. So for the oxidation, I'm going backwards. Zinc's going to zinc 2 plus, and so I write positive 0.76 volts. And then for the copper reaction, it's going as a reduction, so I use the value as is, 0.34 volts. And we saw that before, that's 1.1 volts. So I just add the oxidation and the reduction reactions together to get the cell potential. Now this is all standard, 1 molar concentration and 1 atmosphere pressure for the gases. If I have different concentrations and pressures, I can correct that, and we'll show how to do that later.